Okay, good afternoon. The recording started. How are you doing? Given that a couple of weeks passed and a couple of more weeks will pass before the next lecture, because I hope you will enjoy the Easter break. Before we start, I just wanted to let me see if everything is updated here. I think yes. So you may know this is only the calendar of my lectures. So we have, besides today, we have 3 more because we lost some of the lectures for the elections and etc. So given this delay, the schedule of the second module of the course is changed, and you please check the timetable that has been updated. Probably you already know that. And it has been updated, I think, adding 1 hour on Monday afternoon. So, because in the previous version on Monday afternoon, you had 2 hours scheduled of lectures instead of 3 during my teaching, and now they increased. So on Monday, you will continue with the same timing. I think that's it. Okay, but just check the timetable online and you will see the changes. Very good. Also, I didn't put here the calendar of the exams, but you got a message. So you have also the calendar of the exams. I will also include the dates here, but you got a message on Teams and from the forum in Virtuale. So everything should be all set for you. Just be reminded, given that many of you are Erasmus students who may leave in June, July, and go back, remember that nobody's allowed to take the exam remotely. So just check the calendar if you have already your flight booked, and make sure that you have enough attempts available for the exam, or make sure that you are really in a way to come back if something goes wrong. Okay. As I told you, you are allowed to decline the mark of the exam even if you passed. If you don't pass, of course, you have to repeat it. But you are allowed also to decline the mark if you don't like it. And no problem, it's not registered. If you decline, it's not registered, you can take it the next time. The only thing you are not allowed to do, nobody's allowed, is to take the exam remotely. I am telling you again because I got some messages from some of you asking me about what happens if I fail the first attempt, given that I have to go back in my country, and my reply was sorry. There is nothing I can do for that. Okay, I tried 1 year to make an exception, and I got an admonition from the university, and the exam was cancelled. Admonition, it was not an admonition, just they canceled the exam. So it's not a good experience for you. For me, I mean, it was not a big trouble, but okay, good. Now let's go to the past lecture, which we completed, but I just want to make a recap and to focus on an issue that we didn't discuss about this lecture because it's not included in the PowerPoint. So what was the lecture about? About the Earth system and about an introduction to modeling the Earth system. So we first discussed what are the distinguishing features, the essential features of the dynamics of the Earth system. So how it works, basically. And we said that we can study a single part of the Earth system, or better, we can look at it by taking a wider perspective and in a holistic perspective by looking at the Earth system altogether. And this is what modern models try to do. And then we said that in a way we can look at the Earth system by focusing on exchange flows of matters. And these matters may be, for instance, the carbon exchange, carbon flow between the different parts of the system. And then we said the water cycle. So flow of water within the different subsystems, or we said energy. And basically, these are concepts that are the basis for modeling. So we could model the water cycle, and this is done by hydrology. We could model the carbon cycle, and this is done by biogeosciences, or we could model the energy cycle, energy exchanges. Or we can try to look at it in a holistic way by looking at all the components. And then we moved towards how to model these components individually or comprehensively. How can we model it? And then we said, basically, what we do is to resort to mathematical equations. A model is a tool that gives a quantitative representation of the variables of interest. Quantitative means numbers, and numbers means mathematics, meaning that the result from a model is a number, and therefore it is delivered typically by an analytical relationship. And then we discussed linearity, nonlinearity, and we defined what is linearity, because we said one thing is to write these equations by resorting to linear schemes. Another thing is if we want to model the non-linearity of the system, which is a distinguishing feature, actually. The processes are non-linear. But on the other hand, when we build a model, we need to propose a mathematical scheme, mathematical relationship, which try to simulate the various components of the Earth system. In doing this simulation, one thing is the reality, and beware of the difference. One thing is the reality. Another thing is the model that mimics the reality, tries to simulate the reality through variables. I want to describe temperature. This is my selected variable, and therefore there is a model describing temperature. But one thing is the temperature that every day we can measure through a number given by a thermometer. Another thing is the value that is given by a model. What is the difference between a model and the reality? This may seem like a very trivial question, a very stupid one. Okay, because actually it's clear what is the difference. The model is a tool that makes a mathematical representation. The reality is what we see every day, is the nature. But what is actually, if we really wanted to say what's the difference? Basically, the difference is that the model is an approximation of reality. This is the first thing that comes to my mind. If one asked me, what's the difference between nature and the model representing it? Because in terms of numbers, I mean, we observe nature through numbers. And then in terms of models, we obtain numbers from models. But what's the difference? And the first thing that would come to my mind, again, is the difference is that the model is an approximation. It's not really perfect. Today, we know the term digital twin, which is associated to, let me look at the chat 1 second, because I want to make sure that everything goes fine. And okay. So we, as I said, we are used to the term digital twin associated to artificial intelligence. What is the meaning of a digital twin? The digital twin is intended to be a kind of perfect representation of the reality. Twin means that what we get from the digital model, from the artificial intelligence, is a twin of the reality. But actually, this is like a, how to say, it's like a dream. It's not really a twin. It's an approximation. And you can understand this quite easily because it's, I mean, reproducing the reality through mathematical equations. You know from your background that it is possible only in very idealized conditions. conditions that we don't experience when we try to reproduce nature. So what are the reasons for approximations? What are the reasons for uncertainty? We already discussed them. It's in part limited knowledge. It's in part due to the fact that when we apply this mathematical relationship, there are approximations like numerical approximations. So the digital representation cannot really reproduce the reality also because there are computational errors and many other reasons. And there is also one more reason for making a difference, for uncertainty. And this one more reason is the need that we have to simplify the computation. Because already now, with models that are not perfect, in order to run a simulation of the climate system, only few computational centers in the world have the capability, have the computational capabilities to make it. Because it's really demanding with a huge environmental impact. You may have heard recently the discussion and scientific contribution on the environmental impact of artificial intelligence. Because anytime that we ask a question, there are computers running, producing a lot of noise, and this is a minor problem because these are running in rooms that are isolated and you don't perceive the noise from the external environment. But there is need for cooling and therefore a lot of water, hot water that is released in the sewer system, causing an impact, and there is a huge demand of energy. So basically, even these big data centers, they need to simplify things. And in general, when we make a model, any model, we need to introduce simplifications, either because of the computational requirement or because we don't have a perfect knowledge of it. And therefore, we get a simplification. And basically, what you have to realize and to have really clear in your mind is that any models relies on what we call assumptions or hypotheses. What is an assumption? It's a simplification, is something that you assume to be satisfied when introducing your mathematical equations. And again, these assumptions or hypotheses allow you to obtain something tractable. Linearity is an assumption. So I assume linearity because it makes the model simpler and it makes the model more robust, less prone to unpredictable uncertainties. It's a simpler model that works quite well, and therefore we assume linearity. So beware of assumptions. And today, in the scientific debate, usually assumptions are seen as limitations. This is something that I don't agree with. An assumption is not a limitation. It's something that allows us to get tractable models of the Earth system. Why I am discussing these things with you? Because I already mentioned to you that you have to make a difference, to be able to make a difference when discussing climate change of what the data tell you, so what the nature tells you and what a model tells you. Because one thing is data, measurement, another thing is models. So when somebody says, in the future, we expect 1 meter of sea level rise before 2100. The question would be, are you basing this prediction on data? So you look at the sea level rise in the past, you make some extrapolation, or are you using a model? And if it is a model or live, let me make a better example, because when you talk about the future, we talk about prediction, there is always a model. in formulating a prediction. It cannot be observation because we cannot observe the future, unfortunately, not yet. Okay. So let me make another example. When you listen to somebody saying, in the past 30 years, there has been an increase of 15 centimeters of sea level, then the question should be based on data analysis or based on model simulation, because it's a different story. And if it is a model, again, then the next question is what kind of model, which means what kind of assumptions have been introduced. Again, any model relies on assumptions. So we are getting into modeling, and modeling is essential. It's essential because, as I just said, if we want to make a prediction, we need a model. Okay, we discussed linearity, non-linearity. Let me just, we discussed the tipping points, etc. Let's skip this. Now, I think, also discussed the difference, but I'm not sure if we already discussed it, between deterministic and the stochastic models. Stochastic is a kind of synonym for statistical model. So when you talk about models, in order to better understand what kind of model you're dealing with, and again, understanding is essential because you have to understand the assumptions, you have to understand the limitations. So when trying to reach this understanding, it's useful to refer to classifications, and there are several classification of models. And now I am introducing one. We can split models into categories: deterministic or stochastic. Deterministic means that the model is given by deterministic equation, implying that if you run the model twice by using the same input, you get always the same output. So if you make a prediction of sea level rise up to 2100, and you start from the current conditions, from input data, then you run the model a second time, you get the same result if the model is deterministic. If the model is stochastic, statistical, you get different results anytime that you run it. Why? Because the model accounts for uncertainty, and therefore this uncertainty is something that is random. Remember, uncertainty is, you can associate it to randomness. And therefore, like if you repeat tossing a coin twice, you don't get the same result. Tossing a coin is not deterministic. So if I want to make a model for predicting the result from tossing a coin, I cannot use a deterministic model. I have to use a stochastic model, which means that if I run the model a second time, if the previous time it gave a tail, then the next time can give me a head. Okay. So how is this possible? It is possible because, for instance, in the input variables, the stochastic model can take different values, because the input variable is like the temperature today in Bologna. If I want to make a prediction for the temperature tomorrow or in 1 week from now, the temperature of today is one input data. But of course, I know that I can measure it with uncertainty, like it's 14 degrees now, plus minus 0.5, or more, less than that, plus minus 0.01. So a very tiny uncertainty, but there is some uncertainty. And therefore, a stochastic model tries to run the prediction, to obtain the prediction with a starting temperature of 14, and then the next time it may take 14.001, and the result is different. And this is a representation of uncertainty. On the other hand, there is to say that you need many runs. So this is why you get this figure. So deterministic model, let's do this, because otherwise, deterministic model, you have one-to-one, no uncertainty. In the stochastic model, you get an estimation of uncertainty, but through multiple simulations. So it's many to many. Many input, many runs, and many results. This is essentially the difference, if I wanted to explain it very briefly. And the type of models are not very different. So the equations giving the model can be the same, like the example of the temperature. It's just the input data that changes, or other components of the model that may change. Okay, and now, what kind of equations can we use? And I think we made very briefly the example a couple of weeks ago, but if not, just forget what I'm saying about the bucket model. And the bucket model is a classical scheme that can be used to model the Earth system. But what is the bucket model? It is a model that is based on conservation equations. And now let's introduce these conservation equation, because I think I made the example of the bucket model to explain to you that a model is characterized by input variables, output variables, plus other unknowns, which are the state variables. And on the blackboard, I drawn the example of the bucket model to show that there is the need to relate the input to the output. There is the need to introduce a further unknown, which is giving the state of the system. But let's forget about the bucket model and concentrate again on the equations. These models representing the Earth system are essentially based on conservation equations. What are conservation equations? Are equations that study the processes by imposing, for instance, I give you an example, conservation of energy, because what moves the Earth system is energy from the sun. We already learned that the whole energy from the Earth system comes from the sun. Now, this energy is flowing from inside the Earth system, and we can study mathematically this flow. Like, for instance, let me focus on the water cycle, which is easier to understand. We can mathematically follow the travel of water from the clouds through rainfall to the Earth's surface, and then along the hill slopes to reach the rivers, along the rivers to reach the sea, and then from the sea evaporate. And we can study this movement by imposing, for instance, that the mass of water is conserved, because this is true. Water is conserved in the Earth system. The global mass is conserved. It may change its position, but the global mass is conserved. So we can impose a conservation equation, and in particular, conservation of mass. But this may be not enough, because the unknowns may be larger than one. For sure they are. Because I also need to describe other variables. And therefore, if I need more equations besides conservation of mass, what I can think of? The movement of water requires an exchange of energy. So I can impose conservation of energy, like this energy that is given by water, that is associated to water, for instance, over a mountain. Imagine a drop that falls over the top of a mountain. Then this drop basically looks for minimal energy and therefore starts to go downstream, first along the hill slope. In doing so, this drop loses part of its energy. There is a transformation of energy from potential, which is associated only to the altitude, to kinetic, which is associated to the velocity. So the drop, in order to start, imagine the drop that is fixed over a mountain, to start the travel needs to get some velocity. And this is done through a transformation of energy from potential, which is associated just to the position, you may remember from physics, and is transformed to kinetic. And in moving, there is a loss of global energy through friction. And therefore, the drop moves down. Energy transformation, which doesn't necessarily imply a loss of energy, but there is some friction and there is some loss of energy. But the loss can be computed, described by the model. So I can still describe a conservation equation. If I account for the loss of energy, there will be a loss term in the conservation equation. And then the drop gets to the river. And to the river, the dynamics, the movement, the flow changes. There is a higher velocity. And then there is again friction, because higher velocity means larger friction. And then when the drop finally gets to the ocean, the energy is completely dissipated. But I can still write a conservation equation with loss terms. And then when the drop is in the ocean, then through the energy of the sun, the drop evaporates and goes up again, and the cycle is repeated. So conservation of energy is another thing that I can use. And then if I am interested in also describing water quality, like I want to describe the concentration of organic matter into the water, I can introduce further conservation equations in order to be able to describe these additional unknowns. I use the term conservation equation. Part of the literature uses the term balance equation, because conservation may be a bit misleading, because you may have noticed that there are losses. So somebody may say, look, if there are losses, it's not a conservation equation. And then, indeed, maybe a more correct term would be balance equation. But the moral of the story, the concept is anyway the same. In case of water, we don't have losses. So conservation of mass is the proper term. But even if we have some losses of mass for other matters, by introducing a loss term, we need to introduce a loss term into these equations, and basically the concept remains conservation. Conservation by accounting for losses. I hope that what I'm saying is clear. Okay. Okay, very good. Now, what is the form of these conservation equations? And let's try to inspect the form of this conservation equation again by referring to the bucket model. Okay. So the bucket model is, let's suppose that we apply it to compute river flow, which is an essential variable if we want to study climate. Okay. So basically, the bucket represents a watershed. What is a watershed? It is a part of the Earth's surface which is drained by a given river. Okay. So this is the river with the ramification of the river network. The purpose of the river network is to drain a part of the Earth's surface. So basically what happens is that you get some rainfall here, precipitation, better than rainfall because it may be snow, and then we want a model that predicts the river flow. And we refer to what is called a river basin or a river watershed or a river catchment. It's also called catchment. It is the part, again, of the Earth's surface that is drained by a river. We can, by making a simple analogy, represent the watershed like a bucket. So we have here rainfall, and we have here outflow. We already made this example, but I want to make it more explicit, more details. Okay. First of all, what is this? This is water level inside the bucket, and it's WT. Okay. In the watershed, you have some storage, water that is accumulated okay? And then this storage is given by this additional variable WT. This is unknown, unknown. And this is unknown, unknown. Okay, and this is known. Because we observe distribution. Look, this is very simplified. We ignore the fact that in nature you have also evaporation. So I should, in a way, account also for something that goes directly into the atmosphere from the watershed without reaching the river. And this is evaporation. But here we assume that there is no evaporation. We assume, this is an assumption. Okay. This makes this representation valid, especially for short times, because evaporation is a slow process. But if I want to model the functioning of this watershed for a limited amount of time, this is a reasonable approximation. Okay, we say it's a reasonable assumption, but it's an assumption. Okay, now if I want to impose the conservation of, let me see if the camera is getting the blackboard. Yes. If we want to impose the conservation of mass, it is very simple. We can write that, let me check how much space I have on the blackboard on the, okay. Okay. We can write precipitation minus outflow is equal to the change of storage during time. This is conservation of mass. A question, please? Oh, yeah. Okay. Is this enough? It's okay. Perfect. So precipitation minus outflow, change of storage. Very good. This is very simple. It's conservation of mass of water. On the other hand, we have two unknowns. So how can we introduce a second equation? Well, let's think of it. What could be a second equation? And then I could think of the fact that in order to generate an outflow, I need to employ energy. And therefore, a second equation can be conservation of energy. On the other hand, conservation of energy, I understand that would be non-linear. So let's think of an assumption to simplify things. But let me just try to state the problem with clearer words. So here I have an equation relating conservation of mass is relating a known variable to two unknowns. The two unknowns are Q and W. In order to make the problem solvable, I need a further relationship between, like this one, relating the input to the unknowns or relating the two unknowns between them. Because, of course, if I could, of course, okay, it's not a proper way of introducing my reasoning. But if I could find a relationship between Q and W, the problem would be solvable. Or another relationship between P and Q, or between P and W, the problem would be solvable. So, meaning that if I could identify a relationship relating directly P with W, then P is known, W would become known, and therefore automatically in this first equation, I would add only one unknown. So what I need is a second equation that gives to me either a relationship between the two unknowns or a direct relationship between the input, a known variable, and an unknown. So I have to reduce the degrees of freedom. And what I could think of by reasoning on the nature, on this scheme, is a relationship between Q and W, because it's clear that in a bucket, the higher the storage and the larger the outflow. If you make an experiment, you take a bucket and in the bottom of the bucket, you make an hole. If the bucket is empty, you have no outflow. If you start pouring water into the bucket, you have an increase of storage, and then the larger the storage, the larger the outflow. So this would be an energy relationship. If you relate storage with outflow in a bucket, it's an energy relationship, because storage means energy. The larger the storage, the larger the energy, because energy is proportional to the elevation. Potential energy is proportional to elevation. So water into the tank is not moving, no kinetic energy, but there is potential energy, elevation. And when you have an outflow, you have velocity, it's energy. So clearly, I could think of an energy relationship. And this energy relationship, if I go to the theory of physics, is given by Torricelli's law. And we don't need to learn what is Torricelli's law. I can just anticipate to you that it's precisely a relationship that, by referring to a bucket, gives to you a link between storage and outflow. But with the problem, it's not linear. It's quadratic. Okay, we could use it. But if you go back in time, 100 years, people already used this model, but they didn't have any pocket calculator, not to speak about computers. So they simply thought to introduce a very simple linear assumption. And this linear assumption is this one, WT is equal to a constant K, which multiplies QT. This is linear. This is a straight line if you make a graph of it. So they assumed, hypothesized, a linear relationship between storage and outflow. Now, the system is solvable. It's a differential equation, but it can be also analytically integrated because of this linear assumption. You can make an analytical integration. And analytical integration one time was much appreciated because it's very simple, analytical solution, and is perfect. Why? Numerical results by the PC are never perfect. So this is the essence of the bucket model. Again, we can make an integral of it, but let's forget about it. We are not interested in getting into too many details. What I am interested in the message that I want to deliver to you is, first, the meaning that the model is an approximation, and you understand from here why. Second, the value of the assumptions that make the problem tractable, and you understand here why. Okay, and third, the unavoidable uncertainty that you introduce through these assumptions, which is justified and makes the model different from reality. And finally, the importance of elaborating the model by looking at the real processes. And in this case, it's a physical model. So you look at the real process, you look at the theory behind it. The purpose of the theory, why we elaborate a theory? Because we want to represent nature. and therefore in this case it's a physical process. You look at the theory of physics, and the theory of physics gives you conservation of mass and conservation of energy. Conservation of energy that is simplified. Okay, now these conservation equations can be written in analytical form through the Reynolds theorem, Reynolds transport theorem. Okay, so this theorem is, let me open a Reynolds transport theorem, is basically giving to you Reynolds transport theorem. Okay. It gives to you a mathematical representation of the very simple concepts that I explained to you. It's not our purpose to look at the Reynolds transport theorem in detail. It's our purpose to learn this name so that you know what people talk about when they mention to you the Reynolds transport theorem. It means conservation equations, and conservation equations means very simply conservation of mass, conservation of energy, conservation of any matter that you want to conserve. Can be conservation of chemical reactives. For instance, if you are interested in describing the chemistry of some parts of the system, maybe conservation of carbon. And there is a lot of studies about the conservation of carbon. The theorem is quite a bit complicated, but I want to give to you just an introduction. This is why I give this introduction, not for providing material for the exam, because this is not my purpose. I just want to give you an introduction because I think that even if in this course we don't want to focus much on the math of models of the Earth system can be very complicated. So we don't want to go into the details. But I want to give you a glance, like an idea of what it's about, so that this is why I want to give you this example and to make this discussion that will take to us like 15 minutes. And again, it's not a question for the exam, okay? Just I want to make it clear, but I think it's interesting to have an example. So basically, if we want to write a conservation equation, first of all, we need to identify what is called the control volume. And the control volume is the volume with respect to which we want to impose the conservation. So the bucket, the control volume is the bucket, okay, is the bucket model. And in their system, the control volume may be the whole Earth system. Actually, you will see that we cannot take the whole Earth system as a unique control volume, but in principle, it could be. For the case of a river reach, the control volume may be this piece of river reach that we are considering. And this control volume can be fixed in space or moving in an inertial system of reference. Inertial means that I identify, for instance, a moving control volume like a bubble of water inside a river that moves along the river. In general, we refer in physics to these inertial control volumes. But on the other hand, the bucket is an example of a fixed control volume. Now, in order not to complicate things, let's suppose that this bubble that you see over the screen is fixed in space. Actually, like a river reach, okay? And so, in a river reach or in a bucket, how can we impose conservation, for instance, of mass? And it is in general a very general problem because it's not so simple as we have depicted here, where there is only an input and an output. there could be source terms inside the bucket, like somebody generating water into the bucket. And this is something that we have to take into account. And in general, in the bucket, you have the outflow that is possible only through the hole. But in general, in a control volume, the surface may be permeable to the matter that we want to conserve, for which we want to impose the conservation. So for now, let's start with this figure that you see over the screen. It's a volume which is contoured by a surface as the volume is V, and it's a volume, so it has the units of a cube length, okay? And the contour surface is indicated with capital S, and the unit is, of course, square of length. And then let's identify with S, a portion, an infinitesimal portion of the surface. And let's suppose that in general, there is the possibility of flow through the surface, and then we need to identify the orientation of the surface with a normal vector n pointing outside the volume by convention, okay? So basically, we want to split the surface into small pieces, and for any of these small pieces, we want to know the orientation through the normal vector. Why? Because, of course, if there is, of course, sorry, it's not of course, we need to know the orientation, because if we have some flow moving into this volume, the flow is moving with a certain direction. And therefore, if we want to know the flow through the surface, I need to know the orientation of the surface, because if the flow is parallel to the surface, there is no exchange through the surface. If the flow is perpendicular to the surface, you have an exchange. Okay. 1 second, I just want to see. Yeah, okay, the screen is still there. So I need to know the direction. And then let's, one thing. Why, in your opinion, should I split the surface in small portions? The reason is that these processes that we want to describe are heterogeneous. Heterogeneous means that, for instance, the velocity of the flow inside the volume, the vector velocity is changing in space and in time. But heterogeneous means changing in space. And therefore, it's clear that if I want to model, describe the flow through the surface, I need to consider how this surface is shaped, and the shape changes in time. So I cannot really describe with a unique representation the flow through the surface. Because if this flow through the surface is continuously changing in space, I need to describe point by point. Okay? It's not like here where I have only one hole with a unique direction. If I have another hole here in the bottom, of course I have to make a description of the flow through here and the flow through here. Therefore, I need to split already the surface in two components. And if I have flow through the whole surface because the bucket is permeable, then I have to describe one by one what is the outflow. Because outflow here would be zero. Here I will have a very minor outflow. Here an increasing outflow, and here the larger from here to the bottom. So I need to split the surface in small pieces. Now, let's suppose that, let's look at the variables, okay? Here, let me increase. So vector n pointing outward is the normal vector to a small portion S on the surface S. Okay. Now, let's consider the total amount of an arbitrary property, capital phi here, in units of the property itself. It's if it is mass, it's kilograms. If it is energy, it's a different unit. Okay, so let's suppose that this capital phi is the total amount in the volume V of this property, okay, like mass. Okay, the property can be energy, mass, heat, or whatever, and let lowercase p be the density of capital Phi in a small portion dV of the volume V. So this means that inside the volume, you can have different densities of what we want to describe. Again, heterogeneity. Okay. Perfect. Now, what are the reasons for changes of capital Phi within the volume? The first reason of change can be a source of capital Phi within the volume source term, okay? Or a flux of capital Phi through the boundary, okay? Through the boundary. And this flux through the boundary can happen for two mechanisms. A first mechanism is given by transport. So there is some flow of capital Phi from inside to outside, some flow associated to movement of something, like, for instance, think of if I want to make the balance of heat, and think of water that is flowing from inside the volume to outside the volume, then heat is transported by water. So there is a flow of capital Phi associated to a velocity v of some vector who is governing the outflow. It's a convective transport, convective. And then there is a second mechanism, for instance, for bringing heat from inside to outside. It's convection. There is no movement of any flow, but still there is heat that goes from inside to outside through convection. Okay, so there are two mechanisms, again, that can transport matter from inside the volume to outside, and I have to account for both of them, okay? So if I want to describe the dynamics, which means change over time, of the total amount of the quantity capital Phi inside the volume B, this is expressed by the first left-hand side of this equation, which means derivative over time, which is nothing else than change over time of what? Total amount capital Phi. And the total amount, if I want to compute it, given that the density is changing inside the volume, I have to split the volume in small pieces, and inside each of them multiply density times the volume of the small piece. So here you have density times the small piece of volume. Density, remember, is expressed in units of capital Phi divided by volume. So if I multiply density by an elementary volume, I get the amount capital Phi. Okay, and by summing over the full set of the small volumes, I compute the total amount of capital Phi inside the volume. The sum is an integral. Remember, don't be scared by integrals. The integrals are the simplest of the four operations that we can think of. It's a sum. Okay, so the integral is sum over the volume V of the small pieces of volumes, elementary volumes, times density. And then I look at the change over time. Very simple, at least once one has studied it. So this is what I want to study. The change over time, the dynamics of the total amount of the quantity capital Phi inside the volume V. Very good. Now, at this left-hand side, we have the three components. Let's start from the easiest, the source term. The source term is given by this symbol capital H, is the production inside the control volume of the quantity of interest, capital Phi, production per unit time and unit volume. So once I multiply by the volume, it's capital Phi divided by time per unit time, which is exactly what you find here. So the source term is just looking at what is generated per unit time inside the volume of the quantity that I want to describe. Is there any source of water inside the bucket? And possibly yes. So I split the bucket into small volumes, and for each of them, I look at the sources of water. If I inject water inside the bucket, this is a source term. And here we have the two mechanisms of transport. This is related to some velocity through S, and therefore this is the convective part of it. And this is the convection part. So here, this is easier to be understood with respect to this one, because in this one we have to define what is this new variable capital F. Here, you see that you have the density of capital Phi inside the volume, multiplied by the velocity of the flow through S, and here you have the small surface S, and this is integrated sum over the whole surface. And here, instead, you have to define, as I said, this new capital F is the component along N of flux of P in absence of fluid transport, and is expressed in terms of Phi per unit time and the unit surface S. Of course, in order to solve this equation, we need to define these terms. First of all, we need to define what is the quantity, the matter that we want to balance. Okay, this can be applied to water, can be applied to mass, can be applied to energy, can be applied to heat. And then we have to define the source term, because in general, there are source terms. And then we have to define the velocity of the fluid for convective transport. And then we have to define this term of convection. So this is an example of a mathematical relationship, and you see that it looks already a bit complicated, and it implies a lot of formalisms. But on the other hand, this is necessary. If I want to study whatever process of the Earth system, I have to think of conservation equations. And I think it is instructive because it forces you to understand the correspondence between mathematical relationships and the reality. And referring to examples makes the tractation easier. If you move forward in my lecture notes, there is into a box, there is a mathematical development of this equation in order to make it more tractable mathematically. And this is based on, here there is the example of the bucket model. And for instance, here there is an example of application to the bucket model. So if I want to describe the change in time of the storage into the bucket, so basically what I am describing here, capital Phi becomes the volume of water. So it is an application to mass balance. So capital Phi becomes WT. Okay, this is given by, there is no source term in the bucket, there is no convection, there is only the convective term, which is given by the velocity associated to the outflow. And this can be simply expressed as Pt minus Qt, because you have, when you compute the convective part of it, you have to look for the flow of water through the boundaries of the control volume. So the outflow is this component, but there is also rainfall. Rainfall is getting into the bucket by flowing through the control volume. And therefore, the integral, which gives to you the convective component, is simply given by Pt minus Qt. So this is an example that indeed, this equation that we have introduced, if you start eliminating terms, because you don't have source terms, you don't have convection, and therefore you eliminate another term, then it's a way to simplify it. In this case, it becomes very simple. It is the equation that I introduced as a first example to you. Now, to simplify the equation in general, we can refer to some integral transformations, and then we can call into play the divergence of a vector, and making some transformation of integrals, therefore obtaining a more simplified representation, which is the classical representation of the Reynolds transport theorem. It is this one that you see over the screen, which implies the divergence and a vectorial representation. We forget about this. It is reported here just because some of you may have a very good background in physics and may also appreciate the fact that we, in a way, highlight what is the mathematical treatment of these expressions like the Reynolds transport theorem. But I don't want to get into the details because it's very boring and it's beyond the scope of this course. But on the other hand, I have the feeling that knowing something about conservation equation and their physical fundamentals is important from an educational point of view. And then I think we can move to the next lecture. Do you have any question of what I explained today? No? Okay. But this is science of climate indeed, and therefore it's science of climate change. So the way in which we model climate. And now, in order to get into more details, but with a description that is a philosophy that is essentially narrative, let's look at how climate models are done. And I have here a PowerPoint presentation, climate models. Okay, so we already know why we need models for getting predictions, and we already know a classification which we introduced, because there are many types of climate models. I mean, this combination of equation depends on what we want to describe first, and depends on the assumption that we want to introduce. It depends on how simple we want a model. I think that knowing how climate models work is a fascinating part of this course, because first, they are very ingenious. I mean, they are very complicated. and therefore such complexity is fascinating because it resembles our effort of humans to understand what is nature, what is around us. It's really, I think it's fascinating. But of course, you need to make an effort to see what is exciting behind it. And in making this effort, try always to associate what you see over the screen with what you see outside, because this is what drives scientists and researchers. Observation. Observation that turns into a translation in mathematics in order to be able to make predictions. This is what science does. Observation, making assumptions, which are part of the theory, identifying what is the relevant theory and what are the equations. A theory is a system of equations, is a system of principles, is an organized system of principles, driving concepts, and then equations, assumptions and equations. So we already introduced a possible classification of models, which is splitting the models into categories, and deterministic versus stochastic. Now there is another classification that I would like to introduce to you, and it's a difference between, for the models of physics, so the models of the climate system, which are essentially physical models, the distinction, the difference, the categorization is between empirical models and physically based models. Empirical means that we don't care about the theory. We just want a mathematical relationship that relates, that gives the prediction. It can be derived without referring to the concepts. Think of artificial intelligence. Artificial intelligence doesn't, in general, doesn't look at the equations. It just makes an analysis of data. Think of machine learning, which is a kind of artificial intelligence. Machine learning in a bucket model wouldn't apply any conservation equation. In a machine learning model, you give the input, precipitation, you give observation of precipitation, you give observations of output, and machine learning learns from these observations and then makes predictions without making any conservation equation. And this is reasonable. If you think of it, observation, you relate what you see in terms of input to the output without caring about what is in between. This works. If you think like tossing a coin, the best way of interpreting, making a prediction of the result is taking trials. And then you see that half of the time you get an head, half of the time you get a tail. And therefore your prediction is, if I toss a coin, I have 50-50 probabilities of getting an head or a tail. I have 50% probability of getting an head. This is a prediction. Even if it's uncertain, it's a prediction. And this prediction is derived by simply making some trials and without resorting to a kind of description, physical description of what happens when I toss a coin. And you understand that such physical description would be extremely complicated. In principle, it's possible. I have a colleague who made a physical description of rolling a dice, and it's possible. If you drop the dice from a fixed point over this table, like you fix this starting point of the dice, and you put the dice here, and you give a forcing which is measured to the dice, and then the dice rolls over the table. And from a physical point of view, you can predict it. But of course, it's impossible to get a precise outcome. Why? Because it's extremely nonlinear. Extremely nonlinear. So if you just change a little bit the position of the starting point, even of 1 millimeter, you get a completely different result. And if you have like the resistance of air, when the dice rolls down, and you have a small change in the air density, the results change. So the physical description, the deterministic description is possible, but unfortunately it doesn't hold. And therefore, it's much better to roll the dice several times and say, okay, the probability of getting 1 is 1/6. This is an empirical model. Or black box, as you see here. Input, output, black box. The other possibility is to use the equation of physics. And depending on the process that you want to describe, if you want to drop a body in the void, the physical process works perfectly. The physical description works perfectly, much better than experiments. So we can classify the models in empirical models or physically based models. So what is, if I want to apply this classification to the bucket model, what is the result? Is it physically based or not? On the one hand, you would say, yes, it is physically based because it's based on conservation of mass and conservation of energy. On the other hand, I would say, yes, but conservation of energy is approximated. So it's not really physically based. It's something in between. All of these classifications, usually we try to make classification in black and white. There is also a gray zone. So if I want to classify the bucket model in as an empirical model or a physically based model, I would give it the color of gray. Okay. Okay, very good. So this is our purpose anyway, to get predictions. And we are referring to a long history. And we think that climate models are a recent invention of humanity. Actually, it's some of them were introduced by Greek astronomers, so 3,000 years ago. And then already about 150 years ago, some very simple climate models were introduced, and I will show you an example. And then with computer simulation, with the availability of computers, of course, this discipline increased a lot. And I would say that recently, very recently, in the past 10 years, with the continuous increase of computational power and the advent of artificial intelligence, there has been a marked improvement of these models, which typically are physically based. We don't use empirical models for predicting climate. Why? Because when I mentioned these empirical models based on observations, the problem is that we need observations. Let's suppose that we look at this bucket and we don't have any measurement of rainfall. We just wonder, let's suppose that it rains 100, what is the outflow? And then if I don't have observations, the only possibility is physically based. I apply the theory. So this is why climate models are not empirical. First, because we don't have many observations. Second, because the future will be different, because in the future we assume a CO2 concentration in the atmosphere that is much larger than today's. Therefore, I need to resort to the laws of physics. Actually, when we want to reproduce river flow instead, very often we apply machine learning, we apply empirical models, but because we have a lot of observations. And basically, we refer to a situation which is the same as a situation when we collected the data. But climate models are usually deterministic for this reason. And therefore, you understand physically based, which means deterministic. You understand that uncertainty is a bit of a problem. You understand why climate models are uncertain. Because we have only few data points to check the correctness of models. One interesting thing is why we have so little data, why humans didn't start to measure climate 3,000 years ago, like they measured the position of stars. And it's a curious question. So why humans didn't measure rainfall starting from 3,000 years ago? Probably because rainfall is very local. So it's left to the individual initiative. For instance, in Italy, several observatories started to measure temperature, rainfall, and for instance, the archive of the monks are an essential source of information. But basically, these archives were taken by individuals and maybe communities, but small communities, not organized in a global effort. And therefore, when the communities undergoes extinction or the community in any way ceases to exist, then there is an interruption. So this is why probably one of the reasons why climate is so local. It's not like the stars. It's not like the sea level. But even the sea level, we don't have long measurements. Anyway, now we have instead this need of trying to predict climate, and then we already know that in principle we should reproduce several subsystems. But let's see, let's go very quickly through this because we already know, we already discussed the cryosphere, the hydrosphere, the biosphere, the technosphere. And we already discussed the water cycle, but I want to make an emphasis on this graph because it clarifies first the essential role of water. The climate system is governed by water and energy exchanges, but I mean, water is one of the main behaviors that we have to study. And this is the first consideration. So why I make a focus on water. And second, I believe that this figure is delivering a concept that is amazing if you didn't look at it before, which is the subdivision of water in several components. Keep in mind one thing before I start the description of this very simple diagram, that this is representing water in terms of storage. It doesn't represent flow of water. Okay? And then this is a distinguishing feature of this diagram. I will explain you why. A distinguished limitation. This is just a picture of storage. Like if one now gets a screenshot of the Earth system, of the water in the Earth system, a screenshot freezes any movement, is not represented, you get this. And let's look at the left column, total global water. What you see from here is that of the total volume of water in the Earth, only 3% is fresh water. Okay, so oceans is 96.5%. There are other contribution of other salt waters. Fresh water is actually here is 2.5%. Still, this fresh water is enough to feed humanity, even with an hypothetical increase of human population to an order of magnitude more than today. The problem is the distribution that, you know, there are some places and some times where there is too much water and some places where they don't have any water. But still, if we look at the global picture, 2.5% is enough. And you understand that if we were able to use ocean water without the amount of energy that is required today, this will become something like an infinite good water, which actually now is not infinite. It's not infinite because there are some places where they don't have any water. Okay. Now let's explore the fresh water in the second column. You see here, this is total global, this is fresh water. Fresh water, we have 2/3 of it, so 2% of the global, which is trapped into glaciers and ice caps. Okay. the water that we can use, and there is a remaining 30% in groundwater and surface water 1%. Okay. And then let's make a zoom over surface water. Surface water, there is a part of it, two-thirds again, which is blocking into ground ice and permafrost, and then there are lakes, 20% of the 1% of the 2%. Okay, lakes, and then there is atmosphere, living things, rivers, marshes, soil moisture. So at the end of the story, the part of water that we can use, if we remove also this two-thirds, is 1% of the total. Still, it's enough. Now, why this graph has a limitation, the distinguished limitation? Because it doesn't represent flow, only storage. So from this graph, you may conclude that rivers, who cares? It's nothing compared to the rest. But in rivers, water is flowing. This means that when you get water from it, you can get continuously it. In groundwater, water is not flowing, or it's flowing but with a very limited velocity. And therefore, when you take water from the underground, it takes a long time to be replenished. Actually, in fact, we get much of our water from rivers, even if the volume, the storage is very reduced, but it's flowing. So you see the importance of describing flow. It's not only a description of mass that we need, a description of storage. We need to describe also the flow. And this is what climate models tend to do. Climate models also describe water cycle, okay? You already know that the climate system is driven by solar energy, and you already know that this is the only energy that feeds the Earth system. And I think that we can skip other consideration in the slides because we already know it. And also this one, okay. Yeah, there is, the first one is interesting, and the fact that Earth is heated by sun in an uneven way, and this originates differences in temperature, and differences in temperature mean that there is flow. These differences originate a flow of matters, flow of heat, which implies flow of energy, and flow of water. And these flows take place along the connections between the different parts of the Earth system. And in particular, if you think, we don't look in details at the dynamics of the atmosphere, but in the atmosphere, these differences of temperature originate large-scale movements of air and associated humidity. And this is what originates the perturbation, the winds, and the jet streams also, which are originated not only by differences in energy, but are also originated by the rotation of the Earth around its axis. And that all of these movements in the atmosphere originate what we call the atmospheric rivers. So the movement of water in the atmosphere, which originates the perturbations and originate these processes that are characterizing our fundamental processes in the Earth system. And this gives us a way to think of what kind of equations we can apply. Conservation equations, again, conservation of mass describe these flows in the atmosphere, in the underground, and conservation of energy, essentially. Okay, and let's take into account, and then we make the break, that everything is very nonlinear. Everything is very nonlinear. And therefore, there is the possibility that we have to describe also chaotic behaviors. Chaotic behaviors, as we mentioned, means, and you see, for instance, here, an example of turbulence. Turbulence is chaotic. And this means that for the same input of a deterministic system, or better to say, for an input that looks similar but characterized by very tiny differences every time that we run a simulation, but also in nature. And in some cases, like the flap of the butterfly in Japan, originates completely different outputs because the system is chaotic, it's non-linear. This means that we may need, in order to better understand the system, to run these models several times, or to run different models based on different assumptions to understand what is the uncertainty associated to the assumptions that we introduce. And unfortunately, these uncertainties in a chaotic system may become very large, and we need to take into account this possibility. And taking into account means that you may evaluate the need of testing different assumptions and different models. So not only is the system complicated, but also it's complicated the fact that you may have to try different modeling solutions. But still, these modeling solutions have something in common, which we will discuss after the break. Any question? Okay, so let's meet at 3. I stop the micro and Okay. Okay, so first of all, what are GCMs? Global Climate Models. So these are models that try to reproduce the whole of the climate system and are described by typically conservation equations. A distinguishing feature of these models is the representation over elementary cells, over a grid of elementary cells, which are distributed along the surface of the Earth, but also in the atmosphere and in the underground in general. And therefore, it's a 3D representation. It's not only 2D over the Earth system, it's also over the horizontal direction of the space and also in the vertical direction. Why this representation in grid cells? For the very reason of heterogeneity, which means that these variables are highly varying not only in time, but also in space. So why, when a variable is varying in space, we need a representation in elementary volumes? If you consider the example of the control volume that we saw just a few minutes ago, a control volume that was completely arbitrary, but what we got when we discuss this control volume is the total amount of a given quantity, capital phi, as you remember. So we didn't get any detail on the distribution of this total amount inside the volume. So we said that in general the density is varying, but if we don't have a distribution of the density inside this volume, we need to make assumptions that allow us to account in some way for this heterogeneity, but at the end of the story, the result of the conservation equation is a quantity that is referred to the full control volume. So it's a representation that is valid on average. It's valid for the full control volume. Therefore, if we decided to take as a unique control volume the whole Earth system, as we said at the beginning of today's lecture, we said in principle we could get a control volume that is extended over the whole Earth system, but in this case, the variable of interest, which may be temperature, may be a mass of water, would be representative of the whole Earth system without giving any detail on the internal distribution, on the spatial distribution. Actually, we are interested in describing the temperature in general at the local scale. I want the temperature in Bologna, not only an estimate of the whole global temperature, which is valid on average. If I want a description of the local scale, I need to make this control volume very small. And this is the reason why we see the Earth's system that is subdivided into elementary volumes, because for each volume, for each elementary volume, I get a description that is valid on average. I get one value of temperature, which applies to the whole elementary volume, one value of maybe mass of water, whatever. And therefore, I need to make this representation. What is the size of these grid cells? At the beginning, the size was very large. Even if the model was considered to be detailed, the size of the grid cell was something like 200 by 200 kilometers, and therefore an area that was extremely large. And therefore, the representation that we got was valid, for instance, for northern Italy, or just a few cells over the north of Italy. So the description was very close, as we said. And then with the increase of computational power, we were allowed to make the elementary volumes smaller and smaller. And today we can generate, thanks to the availability of a lot of computational sources for the whole of Italy, a description where the grid cell have a size of 3 by 3 kilometers. This is the highest resolution that we reached over the whole Italy. At the urban scale, where we can run more detailed models, we can reach a resolution of 1 kilometer by 1 kilometer. This is the order of magnitude of the size of these grid cells. But the complication that arises from splitting the Earth system into these elementary cells is not only the fact that there is a multiplication of the number of equations. Of course, any grid cell, depending on the number of unknowns that I want to describe, has to be characterized by a system of equations that may be, for any grid cell, like 5, 6 equations. Think, for instance, if I wanted to apply the bucket model, 2 equations, and with a resolution of 1 kilometer, think of the millions of equations that I could get. This is one reason for complication, for complexity, but it's not the only one. The problem is that these grid cells exchange matters, and therefore I need to describe the flow also between cells in the 3 directions, which means that the whole system of equations needs to be solved simultaneously, because the result in this grid cell depends on the results on the neighboring cells. And therefore, the model is made up by millions of equations. And this is why only few computational centers in the world have the power of running these models. What is the number of cells? Let's make an interrogation very quickly, like number of grid cells in GCMs. Okay, let's look at AI into a 3-dimensional grid containing roughly from 500,000 to several millions cells. And you see here, horizontal resolution. Early models used grids of roughly 500 by 500. I confirm, you know that when looking at artificial intelligence chatbots, you have always to check what comes out. Okay, so this is a recommendation that I already gave to you. And modern models like those in CMIP 5 or 6, these are acronyms used to identify the last generation of models. CMIP stands for Coupled Model Intercomparison Project, because there are several models, several types of models, and therefore there are these projects comparing model outputs. And the last one is CMIP 6, horizontal resolution around 1 by 100 or higher. And vertical layers, atmospheric models typically have 20 to 40 vertical layers. And some high resolution models attempt to use finer grids. Okay, and here it doesn't say the size, but it's about 1 kilometer. And here there are other details. So several millions of which means several millions of equations. Oh, sorry, I was here. Okay, now we already talked about dimensions. We already talked about conservation laws. And here you have some examples of physical quantities that can be described, like energy, momentum, mass, water vapor, temperature, and soil humidity. One important thing, let me look at the next slide because, okay. Let's keep this on the screen. One important thing, during their evolution, climate models increased their complexity. At the beginning, they were meant to describe only temperature. And then an attempt was made to describe other climatic variables like rainfall, like wind speed. And then, in order to complete the representation, given the importance, the strong importance of the connections between the atmospheric system and the land system, then an attempt was made in the last generation of models to also simulate land variables like river flow, like soil moisture, like interaction in general between soil, vegetation, and atmosphere. And therefore, in the attempt also to describe the carbon cycle. And these models are called Earth system models, and instead of climate models, Earth system models, and they are obtained by coupling climate models with what are called land surface models. We still don't have a full coupling with the ground, underground, which is still important because in the underground there is a lot of water stored, and therefore, the contribution of groundwater to evaporation, to transpiration by the plants is extremely important. We are not still there, but today the literature and the media tend to speak, to term these models like Earth system models rather than climate models, because we understood that modeling only climate means introducing several simplifying assumptions that are limiting the reliability of these mathematical representations. Of course, this means increasing complexity, which means that only, as I said, few research centers, computational centers in the world can run these models. And another important consideration that you have always to keep in mind is the reliability of models in simulating these variables. It's different. Models have different performances depending on the variable that you consider. Typically, they are better in simulating variables that are more regular, like temperature. And they have some problems in simulating the variables that are more heterogeneous and more rapidly changing in time, like wind speed. Wind speed is a very local phenomenon. So you understand that it's very complicated to simulate it in a reliable solution. And therefore, you have to always take into account the fact of the reliability depending on also geographical location. There are places in the world which are easier to model. For instance, flat areas are much easier to model than mountainous areas. Mountains are originating a lot of heterogeneity, a lot of turbulence, and therefore making prediction becomes more difficult. So basically, by looking at the model structure, the type of model, the resolution, meaning spatial resolution, you should be able to gain an understanding of what you may expect in terms of reliability. Remember, models are built, as we learned today, over assumptions, which means that they reflect what we think is driving the Earth system. What we believe after our assumption is the evolution of the Earth system. They don't reflect nature in a strict sense. They reflect our understanding, our current knowledge. They cannot reflect what we don't know, of course. Okay, and let me, of course, yeah, the slides help me to remember. Of course, these models, among the input variables, they need to consider also what is our prediction in terms of future emissions. They have to be informed with those prediction scenarios that we already discussed. And this is a relevant driving force for which the models cannot be tested because, of course, we are trying to run them in a setting that is much different, as I already mentioned, with respect to the current reality. And it's not only a matter of CO2 emissions. There are other greenhouse gases that are extremely important, like water vapor, which may increase with an increase of temperature, and then aerosols, etc. Now, this is something that we already discussed, emission scenarios, and whatever, output from the models, input variables. We didn't discuss the time step. We discussed about the spatial resolution, but not the time step. Because these equations, conservation equations, I don't have the conservation equation here, but let me just write back the conservation of mass for the bucket model was this conservation equation. Okay. You see that there is a time step here. Okay. It means this equation describes the change in storage over time. This equation means that you need to inform the model of what is the timing of your prediction. Actually, I use the term time step, which is not really correct, because if the equation is integrated analytically, you get an explicit representation of W, which is a function of PT. Okay. You may get an explicit representation or an explicit representation of Qt. So there is no time step, there is time. So you need to specify the time at which you want to know the prediction. If this can be integrated analytically, if you integrate numerically, you need to approximate. What does it mean, first of all, integrating numerically? Analytical integration means that you get an expression of the variable Wt, which here is expressed in terms of difference, change. If you want to get an expression of Wt, you need to integrate the change, to sum the change. This is why we say integral representation. So if we want to get an integral representation of Wt, we have two ways, analytical, and you have a background in math, and therefore you know what means analytical representation. It means a formula, a relationship. But this is not always possible, because the differential equation cannot always be integrated analytically. So the equation that gives to you the change, the differential equation, not always can be integrated analytically. When it's not possible, we integrate numerically. numerically. What does this mean? Well, I said that the integral is a sum. So integrating numerically means computing the sum. It's in principle straightforward, but what we need to do is to approximate this equation in finite differences. Delta WT divided by delta T equal to PT minus QT. And therefore, from this one, you may get delta WT is equal to PT minus QT times delta T. This is numerical integration. And here you see the time step. So it means that from a continuous representation analytically, I get to a representation at each time step. This is the reason why when you see the meteorological prediction, they say it's not the only reason, but it's one of the reasons why they say prediction for tomorrow, prediction for 2 days, after tomorrow, prediction from 1 week. It's the time step, the prediction. And the time step is defined here. Of course, the smaller the time step, the more precise the numerical integration, because integration in principle should refer to infinitesimal time step. Therefore, the smaller the time step, the more precise the integration, but the more complex the model, because you have to run the prediction more times. So typically, climate models, the most recent one, take a time step of about 30 minutes. Can be 1 hour. So it means that you get a prediction every 1 hour. Okay. And again, the longer the time step and the smaller the precision. Okay. So far, let me look at the next. Okay, perfect. It is the slide that I was expecting. So far, we discussed about the complexity of models, but let me give you an example of a very simple climate model. A very simple climate model, one of the first that have been proposed. And to give the example, let me refer to a figure that is in my lecture. You see, it's the right one. Yes. Here there is a figure which is here. Okay, this one. So, what is the purpose of this model? The purpose is to describe the average temperature of Earth by assuming that the whole Earth system is given by a unique control volume. Given that we want to express the average temperature of Earth, this is possible. Okay, and this indeed is a model that has been proposed, I think, in the past century. And what is the concept? The concept is that if we knew the energy coming from the sun, and we impose the conservation of energy within the Earth system, what is the resulting picture? There is an amount of energy coming from the sun, which reaches the Earth system, and there is an amount of corresponding energy that the Earth system brings, pushes back into the space. This is because the Earth system cannot accumulate heat forever. Otherwise, the temperature will continuously increase. There is an equilibrium. And what are the driving forces governing this equilibrium? Well, first of all, the energy that comes from the sun. And the energy that goes back to the space is governed by the temperature of the atmosphere. The warmer the atmosphere, the higher the amount of energy that goes back to the sun, to the space. And therefore, look, if there is a certain amount of energy coming from the sun and the Earth was completely frozen, the result would be that the temperature of the Earth would increase because being the Earth frozen, there wouldn't be almost any heat going back to space. So the temperature of the Earth increases. As the temperature of the Earth increases, the amount of energy that goes back to space increases as well until you reach an equilibrium. So the idea is, if we were able to quantify the energy that comes from the sun, and roughly speaking, we can do that, we can measure it. And we were able to quantify the energy that goes back to space, which depends on the temperature of the atmosphere, we could study the equilibrium, we could impose the equilibrium. And therefore, we could define the temperature, we could compute the temperature of the Earth. So let's look at the energy incoming. And so there is a quantity S, which is the net solar radiation, is expressed, we already mentioned it, watt per square meter. And we can measure it, we know the number, I give you the number, okay? It's written here in the web page. This energy that comes from the sun is not all of it reaches the ground, reaches the atmosphere. There is a part that is governed by the value of the planet albedo that is reflected directly back into space without warming the atmosphere, without contributing to warming, is reflected back. And it is governed by the albedo. The albedo is the fraction of the energy that is reflected back. So what goes over the Earth system, atmosphere and land, is 1 minus alpha. If alpha is the albedo, again, the part that is reflected back, 1 minus the albedo, 1 minus alpha, is the part that reaches the surface of the Earth system. And if you want to compute the energy, because this is S is per unit surface, but not all the surface of the Earth system is exposed to sun. You have to divide the total surface by 4, which is the area of the intersection, the area of the shadow of the Earth. And therefore, in order to do that, you get an estimate of the amount that really reaches the Earth system. Okay. And now, once this amount reaches, let's say, the surface, then you have a part that is reflected back into the atmosphere, which we can compute, we can prove is proportional to the temperature elevated to the power of 4. Here, temperature comes into play. And a second proportionality constant is the Stefan-Boltzmann equation, which Stefan-Boltzmann constant, which we know, it's defined by numerical experiments. So this means that of this energy that reaches the surface, then you have a part that goes into the atmosphere, and then this part, which is again proportional to the temperature at the power of 4, is split into 2 components. One part that is escaping to space for thermal radiation, and one part that is absorbed and emitted by the atmosphere. And these 2 parts are split according to a coefficient that we call it psilon, between 0 and 1. So this part that is absorbed by the atmosphere, part of it goes back to the ground, and it's computed according to this relationship. And this is where the greenhouse effect comes into play. So the part of thermal radiation that is emitted by the surface, reaches the atmosphere, and comes back into the Earth's surface. And then there is a part that goes to the atmosphere. Now, we want to impose the equilibrium between this quantity that reaches the surface and this quantity that goes back to space, which, as you see, depends on temperature to the power of 4. And then there is this coefficient epsilon. Okay. How can we write this equilibrium equation? In this way. In this way, and I go back to the slides. So here the albedo is called A. I apologize for that instead of alpha. So we have 1 minus A S. It was divided by 4 earlier. Now the 4 is brought here at the right-hand term. And pi r square, r is the Earth radius, and pi r square is the cross-sectional area of the Earth. Okay, it's the area of the circle. At the right-hand side, you have the surface of the sphere, 4 pi r square. And from here, you understand why the number 4, because it's the ratio between the cross-sectional area of the Earth and the area of the sphere. Okay, so here you have the area of the sphere. You have here the Stefan Boltzmann constant, temperature to the power of 4, and then there is a condensed epsilon, which results from the combination of these two components, 1 minus epsilon plus epsilon, and it's a coefficient that is called, let me see here, effective emissivity, epsilon effective, and here there is a link in Wikipedia, effective emissivity due to the atmosphere. And you see here there is a further link, zero-dimensional models. This is a zero-dimensional model. It's not a model which gives variability of variables temperature in the 3 directions of space. It's just one value, zero-dimensional model, okay? And here you can see the numbers. The average albedo of Earth is about 0.3. S, solar constant, it's about 1300 watt per square meters. And T is the Earth's average surface temperature. The Stefan Boltzmann constant, here you see the value, and epsilon is the emissivity of the atmosphere. Okay, let's forget about the details. And therefore, here you get this equation. It is the same that you have seen over the slides here, but with different symbols, okay? You see epsilon F and albedo alpha. Now, we have all the numbers to be substituted into this equation. The only unknown is temperature. And we can get an explicit expression for temperature, the root to the fourth order root of 1 minus albedo S divided by 4 sigma epsilon F. And if you solve this equation with the numbers that are indicated, you get the average temperature of Earth of 15 degrees, which is amazingly accurate. It's precisely the average temperature of Earth is about 40 dot something degrees. And therefore, it's amazingly reliable. And this is a model that was already applied more or less 100 years ago. And this is, I think, a very good example of a conservation equation. You may have missed some of the details. In particular, I went very quickly through the computation of the epsilon efficient. So emissivity, efficient emissivity coefficient. But I mean, it's if you just make some computation about here, you see that you can combine these different two components by introducing an equivalent epsilon, which allows you to combine these two components. And but I mean, the concept is very clear. It's a demonstration of what is the implication of using a large control volume, that you get a unique value. You don't get from this equation the temperature over Italy, the temperature over the United States, or over whatever location in Africa. You get an average. But it's a very good example of a conservation equation, very simple, that allows you to get a very meaningful result. And it allows you to understand that if you apply the same equation at the scale of an individual grid cell, it gives to you a local estimate, with the complication that if you apply it to a grid cell, you have to consider also the flow of heat from the neighboring cells. So you cannot resolve one by one these cells, but you need to resolve them simultaneously. And you have to consider the local variability of the albedo, etc. Of course, here there are several simplifications, assumptions, which are implicit, like there is no consideration here for the wind speed, which is influencing the temperature. It is influencing emissivity. This is something that is very simplified, but still, I believe it's a very good example. Let me go back to here. Here you see all the numbers, the resulting equation, and then everything, and then the solution. Now, let me just look at the next slide. Okay, emission scenarios. Okay, emission scenarios, we already discussed them. I want now to give you a couple of additional information. First of all, there are linked in my webpage several videos, because over the web you can find a lot of information about these models, which are continuously evolving. And therefore, beware that if you're interested in becoming an expert about these topics, you have to stay continuously updated, because the discipline is evolving. First thing, and already the links that are in my webpage, which are 3 years old, more or less, some of them I checked today, and some of them were disappeared because they have changed. It is continuously evolving. A second thing I wanted to give you as a useful piece of information. We mentioned several times the complexity of these models, which can be applied only in few research centers into the world. Actually, there is a way to simplify the application of these models, because they can be run at the local level and without the need of applying the model to the whole Earth system. How this can be done? Well, what you can do is, for instance, if you have a large region, and this is what we usually do actually, if you have a large region to cover with a model, you can start with the model with a very large grid. And then you get a first simulation. Okay. Now, let's suppose that you are interested in the spatial variability inside this grid, which you don't have after running this model, because you get, for instance, for temperature, only one value. So there is no information on the spatial variability. On the other hand, you get from the neighboring cells the information about temperature in all of them. Okay. And then you get your information in temperature here. But now I want to focus on change the color on this location here. I want to get my temperature there. So what I can do is to use these values computed in the large grid as initial conditions. So I start a new simulation which refers only to this grid, which is subdivided in a smaller grid. So I increase the resolution of the model only in this grid cell, and I use the results from the larger scale computation to inform the small scale model. I use the result of the large scale simulation to provide the initial conditions and the boundary conditions for running a small scale model. Initial and boundary conditions means the starting value of the simulation, and more or less. Means that I start my simulation from these large scale results and then I refine it. And these are called regional climate models, RCM. And this is what meteorological service do. They look at the simulation of global models, and then given that they want to know sorry for the Italian, but when I'm tired it comes out. If they want to know the meteorological prediction for Bologna, they start from the simulation of the global model over Italy. And then in the region around Bologna, they run another simulation at a smaller scale. Now, this is what we do. And this kind of small scale regional simulation is applicable only with a relatively limited computational power. And the next lecture, in 2 weeks from today, I will give you a very short example of how, even on your PC, you could run this kind of small scale simulation. Of course, what you need is the large scale simulation as the input data. I think for today, that's it. If you have any question, I am here.